All right, this is a mini lesson on summations, how to add things. When you see stuff like what's on this slide, you think, horrible. What does that mean? But all this is a fancy way to add. It's fancy adding. It's not hard to do. The notation's unfriendly, but the concept is as simple as adding. This can be taught in elementary school. You can teach this to kids in grade 3, grade 4. It can be done. And I know that for a fact because I've done it. So this is useful. This is more useful than anything else you can learn first year math. How to work with summations, how to think about summations, and just the general problem solving process that you go through in these elementary sums are extremely powerful. First, the notation. The sum from I equals 1 to 9 of A sub I. Let's unpack what that notation means. I is being used as an index or as a counter. It's just to track the label of the object number that we're on. A sub I would be the object that we're adding. A1 is the first object in the set. A2 is the second object in the set. A3 is the third object in the set. These objects may be drawn from a list, like from an Excel table, or they may be created by a function. So A sub I may be given by f of I, like f of x. You plug in an input for that, and you get an output out. So there's different ways of constructing the individual terms that will be added together. Sometimes they're just there, and sometimes they come about by construction through a function. I equals 1 means we're starting at the first element of objects, the first label. Sometimes the sum will begin later. We'll start adding the fifth one. We won't add number 1, 2, 3, and 4. We'll just start adding from 5, 6, 7, 8, and so on. The 9 up there says that we're going to stop adding once we get to the 9th element. So if we put it all together, the sum from I equals 1 to 9 of A sub I means A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus A7 plus A8 plus A9. Just telling us to add the first 9 things together. And the labels of all those things are A1 to A9. You can also use a function notation. We can say the sum from I equals 1 to 9 of f of I is f of 1 plus f of 2 plus f of 3 up to f of 9, all added together. Let's think about adding something really simple, like just numbers, simple numbers, like the first 10 numbers. What's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10? How would we add those up without actually adding them up? Because you can add them up and get the answer, 55. But I didn't actually add them to get that answer. There's a way you can get that answer, like add the first 12 numbers together. The answer is going to be 6 times 11, 66. How? I'll show you. So this is probably the first new thing you've learned about adding since elementary school. You haven't learned anything new since. It's all been about other things. So we're going way back. That's why I said you can teach this to kids in grade 3. We're going way back to early elementary school. To add these numbers up, you do 1 plus 2, 3 plus 3, 6, plus 4, 10, plus 5, 15, plus 6, 21, plus 7, 28, plus 8, 36, plus 9, 45, plus 10, 55. So it's a slow process. How we could add them differently is I'm going to give that sum a name. I'm going to call that sum S. So S is equal to 1 plus 2 plus 3 all the way up to plus 10. You know that the order of adding things does not matter. Like 7 plus 5 is the same as 5 plus 7. If I take all these numbers and add them in the opposite order, so starting at 10 and ending at 1, you know that the answer is not going to change. So 10 plus 9 plus 8 all the way to plus 1, that's going to be the same thing. That's going to be the same S. I'm going to call them both S. Let's add S plus S together, like columns. So S plus S, we're going to have 2S is equal to, I got to make sure that looks like an S, not a 5. 2S is equal to Look at the first column, 1 plus 10, 11, plus 2 plus 9, 11, 3 plus 8, 11, 11, 11, 11, 11, 11, 11, 11. Each column is 11. 8 plus 3, 6 plus 5, 4 plus 7, each of them add to 11. How many 11s do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 of them. Now we're going up a little bit into multiplication. We're going up a grade. So adding 11 10 times, that's the same thing as 10 multiplied by 11. So 2 times what I want is 10 times 11. I don't want 2 times what I want, I just want what I want. So I'm going to divide both sides by 2. So my sum is equal to 10 times 11 divided by 2. Then I can divide 10 by 2, so that's 5 times 11. I gotta make sure it looks like a 5 because it looks like too much like an S. So 5 times 11, which is the wanted 55, which was obtained without actually adding the numbers together. You might say, so what? In the time it takes to construct this, you could have just added the damn things together. Okay, now what? Add the first 100 numbers together. How are you going to do this? You're going to add 1 plus 2 plus 3 plus 4 plus 5. Now, hold off on the question, why would I care to add the first 100 numbers together? I'm telling you now that you do care. You do want to be able to add things quickly. Or at least be able to write a code that would add things quickly and know how that code works and know how why it does what it does and why it sometimes doesn't do what it's supposed to do. Here's how you can add the first 100 numbers together intelligently. I'm going to call that sum S. 1 plus 2 plus 3 plus 4 plus dot 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 plus. I'm putting the dot 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 there because I don't want to have to write out all 100 numbers. I know I'm going to have a 97, a 98, a 99, I'm going to have 100. And I also know that the same sum can be obtained by reversing the order of addition. But S is also equal to 100 plus 99 plus 98 plus 97 plus dot 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 plus 4 plus 3 plus 2 plus 1. Now I'm going to add them together. I'm going to go S plus S, adding in columns. 100 plus 1 is 101. 99 plus 2 is 101. 98 plus 3 is 101. 4 plus 97, 101. Every single one of those pieces in the dot 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 is going to be 101. 4 plus 97, 101. 101. 101. 101. Notice that we have 100 terms from 1 to 100. So we have 100 101s. So 2 times S is equal to 100 times 101. Divide both sides by 2. 100 times 101 divided by 2 is 50 times 101, which is 5050. 5050. Without adding. I don't think there's any, we did add, we just added 1 plus 100 and 2 plus 99. That's all the adding we did. We had to do some multiplying and some dividing. But definitely faster than trying to manually add it. What's really nice about this is if you can replace that 100 with a million or a billion or a trillion, and it doesn't take any longer. It's the same length calculation. So we took a very long calculation and reduced it down so that it doesn't matter how big the number is. The calculation is this, it scales the same. It's fast. What if n isn't specified? What if there is no final n? Like this said stop at 100. What if it doesn't say stop at 100? It just says stop at n. Well, here's how we do that. S is equal to 1 plus 2 plus 3 plus 4 plus dot dot dot. Now I know my last number is going to be n. When n was 100, my previous to last, my second last number is 99. Now, I don't have an ability to say like a 99, but I can say what the second last number is. It's one lower than that. Now, how do I make one lower? Well, I subtract 1. So it'll be n minus 1. How about prior to that one? N minus 2. And I could do n minus 3 and so on, but I'll just stop there. Next, I can reverse the order of the sum. It's also equal to n plus n minus 1 plus n minus 2 plus n minus 3. I'll put brackets around these so they're a little bit easier to group together. Plus dot 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 plus 3 plus 2 plus 1. Now add all the pieces together in columns. What is s plus s? It's going to be n plus 1 plus 2 plus n minus 1. So 2 plus n minus 1 is just another n plus 1. 3 plus n minus 2 is just n plus 1. 4 plus n minus 3 is n plus 1. N minus 2 plus 3, n plus 1, n plus 1, n plus 1. We have n of these terms. So 2 times s is equal to n times n plus 1. N things added together. So there's n of these. On the previous example, I should really highlight that. There's 100 of those. And then we can do one last step. We can get s all by itself by dividing both sides by 2. N times n plus 1 all over 2. This was discovered by Friedrich Gauss. Friedrich Gauss, I believe, was in, I can't remember if he was in grade 4 or grade 5, but he was in elementary school, and his teacher punished him for being bad. He was talking in class and being disruptive, and his punishment started by adding a bunch of numbers together, and then to come back and bring it to the teacher and say, okay, I'm done. So first add the first 10 numbers, add the first 100 numbers. And I don't remember the details of the story, but at some point the teacher said add some gigantic list of numbers to get like the first 1,000 numbers. Gauss sat down, came back in a few minutes, said, here it is. And the teacher was like, how am I going to check this? Like, he's probably just teasing me. This isn't right. But it was right. And he discovered this formula in exactly this way. What else can you do for fancy adding? So this is another example, and it's a more powerful example, a more useful example. It's called the sum of a geometric series. You'll come across this in finance, come across this in different areas. I'll start with a simple one where the Kalman ratio has this fancy name. I'm looking at a sum that is the sum of the first 10 powers of base 2. So 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3 plus 2 to the power of 4 all the way up to 2 to the power of 10. So that'll be 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 plus 256 by 5 plus 512 plus 1024. Adding all those up, which isn't impossible, but there's an easier way. The easier way is a little bit different. We're not going to reverse the order of the sum. We are going to say s equals that sum. But instead of saying just reverse the order and add them together, I'm going to say, what is 2 times s? I'm going to double it. So 2 times s is 2 times each of those pieces. So 2 times 2 to the power of 1 is going to be 2 to the power of 2. 2 times 2 to the power of 2 is going to be 2 to the power of 3. I'm just distributing and using exponent laws. So from this term to this term, for example, that's 2 to the power of 1 multiplied by 2 to the power of 3. Exponent laws says that's 2 to the power of 1 plus 3, which is 2 to the power of 4, this term there. So we're just expanding it out each one multiplying the 2 in all the way through. Now what we'll do is we'll take 2s and we'll subtract 1 times s from that. We'll do it in columns. So that's going to be 2 to the 2 plus 2 to the 3 plus 2 to the 4 plus, I'm going to do the subtraction carefully, 2 to the 6, 2 to the 7, 2 to the 8, 2 to the 9, 2 to the 10, 2 to the 11, minus 2 to the 1 plus 2 to the 2 plus 2 to the 3, 2 to the 4. I'm just making a copy of the original s. Oh, 7, already did the 6. Okay, so I'm subtracting those pieces and look what happens. I get 2 to the 2, canceling 2 to the 2, 2 to the 3, 2 to the 3, 2 to the 4, 2 to the 4, 2 to the 5, 2 to the 5. Look at that. All these pieces are canceling out. Now what's left? What has not been destroyed? So I have 2 times s minus 1 times s is equal to 2 to the power of 11 minus 2 to the power of 1. 2 times something minus 1 times something is just 1 times that thing. Like 2 apples minus 1 apple is 1 apple. So s is equal to 2 to the 11 minus 2, and that's it. So we don't actually have to do much adding. We would just do 2 to the power of 1 higher power. Instead of 2 to the power of 10 being our final power of 2, we do 2 to the power of 11 and then subtract 2 from that. It's kind of amazing. What if it's not 2 though? What if it's not 2 to a power? What if it's r to a power? Where r could be 2, could be 3, could be a half, could be a third. What do? Well, we do the exact same thing. R to the 1 plus r to the 2 plus r to the 3 all the way to r to the 10, we call it s. Now instead of multiplying s by 2, I'm going to multiply it by r. So that's the trick. You multiply it by whatever r is. Then you distribute using exponent laws. You get r squared all the way up to r to the power of 11 and then subtract. So I'll write down those pieces. We have r squared plus r cubed plus r to the 4 plus r to the 5 plus r to the 6 plus r to the 7 plus r to the 8 plus r to the 9 plus r to the 10 plus r to the 11. And we're subtracting the original s minus r to the 1 plus r to the 2, r to the 3, r to the 4, r to the 5, r to the 6, r to the 7, r to the 8. Okay, now where was I? Yeah, we're subtracting original s, so r to the 8, plus r to the 9, plus r to the 10. And then most of the stuff, again, cancels out. Since we're subtracting the same thing top and bottom. And what we have left, we have r times s minus s is equal to r to the power of 11 minus r. Then I'm going to common factor s out. So we have s times r minus 1 is equal to r to the 11 minus r. Then I'm going to divide both sides by r minus 1. So the sum, the thing we're after, is r to the 11 minus r, all over r minus 1. This is sometimes written, so that's a good answer, but it is sometimes written as, instead of doing rs minus s, sometimes they do s minus rs, so just the different order of subtraction. And if you do it that way, you'll get the sum is equal to r minus r to the power of 11 over 1 minus r. Or you could common factor an r out of the top. So you have r times 1 minus r to the 10 over 1 minus r. I know you can't cancel those. There's no canceling. So there's 3 different formats that this final answer can be written in. You're likely to use it in the last format, but you may also use it in the first format. What happens if you don't end the sum at 10? What if you end the sum at n? So I'll let you do this on your own, but what the final answer would be, so you see that 10 there? Just replace that with an n. So r times 1 minus r to the 10 over 1 minus r. Oh, r to the n, sorry about that. R to the n over 1 minus r. And you'll come across, oh, and one more thing, you'll come across different variations of this. Like you'll have the sum from I equals 1 to n minus 1 of a times r to the I. And it'll look a little bit different, etc. But they all follow the same type of format. They're all types of geometric sums. Sum of a geometric series. It can appear in many different formats. So this one has a slightly different formula, and there's just so many there's so many different formulations of it that I'm not going to exhaustively write them all down. But this is how they come about. They come about through this fancy adding strategy, and that's not part of Math 1229, not Math 1229. But it is something that you may see in your future courses, so I think it's useful to know a little bit about this before you go into any second year courses for sure. See you next time.